Hello, welcome to my channel Nightlight Science Stories. Today we look into the abyss of the future. For decades, we believed the story was written. We thought the universe would end in ice, a cold and lonely heat death, where stars simply fade away into eternal darkness. But new data has emerged from the deepest shadows of the cosmos, shaking the very foundations of astrophysics. The script of the end times is being rewritten right now, and the ending is not what we expected. Imagine a force so vast it pushes galaxies apart, stretching the fabric of reality itself. We call this dark energy. Until recently, we assumed it was a constant, an unwavering engine driving the universe's expansion forever. But what if this engine is running out of fuel? What if the force that keeps the darkness at bay is actually dying? If this is true, the destiny of existence is not a slow freeze, but something far more violent and sudden than we ever dared to imagine. To understand this shift, we must first understand the invisible ruler of our cosmos. Dark energy makes up roughly 68% of the universe. It is the mysterious pressure that counteracts gravity. Since the late 1990s, the standard model of cosmology has relied on the idea that this energy density remains the same over time. It was the cosmological constant, a number that Einstein once doubted, then accepted, and which we thought was final. But science is never truly settled. However, the universe is a place of constant flux, and nothing may be truly permanent. Recent observations from the Dark Energy Spectroscopic Instrument, known as DESI, have hinted at a glitch in this constant. The data suggests that the strength of dark energy might be weakening as the universe ages. It is like a car that has been accelerating for billions of years, suddenly easing off the gas pedal, allowing the friction of gravity to finally take over the steering wheel. If dark energy is indeed decaying, the implications are terrifyingly beautiful. Instead of an eternal lonely expansion where galaxies drift out of sight, the universe could eventually stop expanding altogether. Gravity, the patient sculptor of the cosmos, would begin to pull everything back together. The distant galaxies would turn around and start rushing towards us. The night sky, currently dark, would become increasingly bright and intensely hot as space itself compresses. This scenario is known as the Big Crunch. It is the reverse of the Big Bang. All matter, all energy, every memory of every civilization that ever existed would be compressed back into a single point of infinite density. But this is not just about the far future. It changes how we understand the present. If the vacuum energy is not constant, then our understanding of fundamental physics, from the quantum level to the galactic scale, is incomplete and needs revision. The concept of a dynamic dark energy forces us to reconsider the work of the giants who came before us. When Einstein introduced the cosmological constant, he did so to keep the universe static. When Hubble showed the universe was expanding, Einstein called his constant his biggest blunder. Ironically, if dark energy is changing, Einstein's blunder might have been discarding the idea that the vacuum of space itself is a dynamic living entity that evolves with time. We are now looking at a universe that breathes. It exhaled with the Big Bang, expanded with the breath of dark energy, and now, perhaps, it is preparing to inhale. This cyclical possibility aligns with ancient philosophical models as much as it does with cutting-edge string theory. The idea that time itself might have a direction that can be reversed or halted creates a paradox that challenges the linear perception of human consciousness and our place in history. The evidence for this decay comes from measuring the light of millions of galaxies and quasars. It is a map of time, stretching back 11 billion years. By looking at how these objects are distributed, scientists can reconstruct the expansion history of the universe with unprecedented precision. The subtle deviations found in this map are small, mere fractions in the data, but in cosmology, a fraction changes the fate of trillions of stars, and the ultimate end. These measurements rely on baryon acoustic oscillations, which are essentially sound waves from the early universe frozen in the distribution of matter. Think of them as cosmic rulers of a standard length. By seeing how big these rulers appear at different distances, we determine how much space has expanded. As we analyze the latest batch of this deep space data, the pattern emerging suggests a deviation that standard theories struggle to explain without a new model. Why does this matter to us, sitting on a small rock orbiting an average star? Because it tells us that the laws of physics might not be the same everywhere or everyone. If dark energy evolves, it could mean that the constants of nature are actually variables. The speed of light, the strength of gravity, the charge of an electron. Could these also be slowly drifting over eons? We might be living in a specific season of the universe, unaware that winter is coming. The DESI results are currently at a statistical confidence level that demands attention but not yet absolute certainty. In scientific terms, it is a sigma level that makes physicists lose sleep. If confirmed by upcoming data, it would be the first major crack in the standard cosmological model in 20 years. It suggests that our simple lambda CDM model, which has served us well, is just an approximation of a much wilder and more complex reality. Let's delve deeper into what decaying dark energy actually looks like mathematically. It implies a scalar field, often called quintessence. Unlike a constant, a scalar field can roll down a potential energy hill, changing its value. Imagine a ball rolling down a slope. As it moves, its speed and energy change. If the universe is filled with such a field, the expansion rate would naturally vary, slowing down or speeding up depending on the field's position. This quintessence model brings a dynamic quality to the void. Empty space is not just empty. It is filled with a fluid that has its own behavior. Some theories even suggest that this field could eventually become negative. If dark energy becomes negative, it would actively work with gravity to collapse the universe. This transition from expansion to contraction is not instant. It is a cosmic braking maneuver that takes billions of years to complete. But there is another possibility, even more stranger than the Big Crunch. It is called the Big Slurp. If the dark energy field changes, it might trigger a phase transition in the Higgs field, the field that gives particles mass. A bubble of true vacuum could form somewhere in the cosmos. This bubble would expand at the speed of light, rewriting the laws of physics and destroying everything in its path. It is a cosmic reset button pressed by instability. While the Big Slurp is a different mechanism, the instability of dark energy makes all these catastrophic scenarios more plausible. We used to think we were safe for at least another 100 billion years. But if the decay is rapid, the timeline shortens. The universe might be much closer to the end of its life cycle than we calculated. The stars we see tonight might already be ghosts in a dying expansion, their light taking eons to tell us the bad news. This uncertainty is what drives the current excitement. For the first time in a generation, we don't know what happens next. The end of history for the cosmos has been canceled. We are back in the realm of exploration and mystery. Every new photon captured by our telescopes is a clue in a cosmic murder mystery where the victim is the universe itself, and the prime suspect is the very energy that was supposed to save it. The scientific community is now racing to verify these findings. Other telescopes, like the Euclid mission and the upcoming Roman Space Telescope, will join the hunt. They will map even more galaxies, look even further back in time. They are trying to find out if the DESI signal is a fluke, a systematic error in our instruments, or the first whisper of a new physics that will redefine our existence. The stakes could not be higher. As we close the first chapter of this investigation, we must reflect on our position. We are observers in a system we cannot control. We are trying to measure the heartbeat of a giant from the inside. If the universe is indeed slowing down, it connects us to a cycle of birth and death that feels almost biological. It removes the cold indifference of eternal expansion and replaces it with a dramatic, fiery destiny. This brings us to the edge of known physics. To understand where we are going, we need to look closer at the discrepancies we are seeing right now. The clues are hidden in the way galaxies cluster, in the way light bends, and in the faint glow of the Big Bang itself. As we move forward, we will dissect the specific anomalies that have led us to this conclusion and explore the alternative theories fighting for dominance in the dark halls of academia. To grasp the magnitude of the DESI findings, we must step into the battlefield of modern cosmology. For years, there has been a silent war between two groups of scientists. One group looks at the baby universe, the cosmic microwave background, which is the afterglow of the Big Bang. The other group looks at the modern universe, measuring exploding stars and pulsating lights. The problem is simple but disturbing. Their numbers do not match. They are measuring the expansion rate of the universe, known as the Hubble constant. The early universe team predicts a specific speed based on our standard model. The modern universe team measures a significantly faster speed. This discrepancy is called the Hubble tension. It is not a calculation error. Both sides have checked their math thousands of times. It suggests that something fundamental is missing from our picture of reality. We measure the universe using the cosmic distance ladder. We start with nearby stars, use geometry to find their distance, then find standard candles like Cepheid variables whose brightness helps us measure further out. Finally, we use type Ia supernova, massive explosions that always burn with the same brightness, to measure the deepest distances. This ladder has been our trusty tool for decades, building the map of the cosmos rung by rung. But now, the ladder seems to be bending. The DESI data introduces a twist. If dark energy is decaying, it might explain why these two measurements don't align. Maybe the expansion rate was different in the past than it is today, not just because of gravity, but because the vacuum energy itself has changed. This would solve the Hubble tension, but at a terrible cost: the loss of the stability of the laws of physics themselves. In the equations of general relativity, dark energy is represented by the letter W, the equation of state parameter. For a constant dark energy, W must be exactly -1. This number, -1, is the anchor of our reality. It means the density of dark energy never changes, no matter how much space expands. It is the steady heartbeat of the lambda CDM model. If W is -1, we are safe. The universe expands predictably forever. The DESI results, however, suggest that W is not -1, or rather, it is not always -1. It seems to be evolving. In the deep past, it might have been different. This variation implies that W is a function of time, not a constant. A variable BU opens the door to exotic forms of energy that we have never seen in a lab. It suggests space is filled with a quintessence field that is slowly rolling down a cosmic hill. When W deviates from -1, the behavior of the universe changes drastically. If W is greater than -1, the dark energy becomes weaker over time, leading to the big crunch we discussed. But if W drops below -1 into the realm of phantom energy, the expansion becomes violent. It would tear apart galaxies, then solar systems, then planets, and finally atoms themselves in a big rip. The current data from DESI leans towards the first scenario, a weakening, a value slightly above -1. This is less violent than the Big Rip, but more melancholic. It implies a universe that is running out of steam. The anti-gravity that pushed the galaxies away is fading. It is as if the universe is tired of expanding. This fatigue is measurable. We are detecting the slowing pulse of the cosmos in the distribution of galaxies. Let's talk about the machine that revealed this secret. The Dark Energy Spectroscopic Instrument is a marvel of engineering. It sits atop the Mayall telescope in Arizona. It contains 5,000 tiny robotic positioners. Every 20 minutes, these robots reconfigure themselves to capture the light of 5,000 new galaxies simultaneously. It is a massive automated eye that eats the sky, processing more data in a night than we used to in a year. DESI is building a 3D map of the universe that is unprecedented in scale. It doesn't just look at where galaxies are. It looks at where they were. By capturing their redshift, it sees them at different epochs of cosmic history. It slices the universe into time periods, allowing us to see how the expansion rate has evolved over the last 11 billion years. It is like making a movie of the universe's growth, frame by frame. The key to DESI's precision is baryon acoustic oscillations. These are the fossils of sound waves. In the very early universe, before stars formed, the cosmos was a hot soup of plasma. Sound waves traveled through this soup, creating ripples of density. When the universe cooled, these ripples froze in place. They determined where galaxies would eventually form. Today, we see these ripples as the preferred distance between galaxy clusters. This distance is a standard ruler, roughly 500 million light-years across today. Because we know how big this ruler should be, seeing how big it appears in the sky tells us exactly how far away those galaxies are and how much space has expanded since then. DESI measures these rulers across time, and the rulers are telling us that the expansion is not behaving as the constant W equals -1 model predicts. The rulers are fitting a different curve. The statistical significance of this finding is currently around 3.9 sigma when combined with other data. In physics, 5 sigma is the gold standard for a discovery. But 3.9 is dangerously close. It is far beyond a simple curiosity. It is the level where skepticism turns into nervous excitement. It means there is a roughly 1 in 1,000 chance that this is a fluke. Those are odds that no gambler would bet against when the stakes are the fate of the universe. This tension is creating a revolution. Conferences are buzzing with new theories. Is it modified gravity? Is it interacting dark sector? Is it primordial magnetic fields? The door that Einstein closed with his cosmological constant has been kicked open. We are realizing that our standard model might just be a spherical cow, a simplified approximation that works for easy problems, but fails when we look at the complex reality of the deep cosmos. This brings us back to the philosophical way of the discovery. If the universe is not constant, it means it has a life cycle. It is not a static stage where events happen. It is a participant. A decaying dark energy implies that the universe spends its energy to expand and eventually exhausts itself. It mirrors the laws of thermodynamics that govern our daily lives. Entropy increases, energy dissipates, and systems eventually wind down. Why should the universe be exempt from the cycles of nature we see on Earth? Trees grow and die, civilizations rise and fall, stars ignite and burn out. Perhaps space-time itself is mortal. The idea of an eternal, unchanging expansion was comforting because it suggested a forever. But a cyclical universe, one that expands and collapses, suggests something even more profound: a heartbeat, a universe that lives, dies, and is perhaps born again. Some theorists are already looking beyond the Big Crunch. They are dusting off old theories like the Big Bounce. If the universe collapses, does it reach a singularity and stop? Or does quantum mechanics intervene, preventing a total collapse and causing a rebound? A new Big Bang. If dark energy decays and triggers a collapse, it might be the mechanism that resets the clock, creating a new universe from the ashes of the old one. This is the Phoenix universe model. It implies we are not the first iteration of existence, nor the last. We might be living in cycle number 1 trillion. The decay we are detecting with DESI might just be the first sign of autumn in the cosmic year. The summer of expansion is ending, and the winter of contraction is approaching, necessary for the spring of a new creation. It turns cosmology into a story of eternal return. But before we get lost in dreams of rebirth, we must face the cold data again. The decay is not yet proven to be a smooth curve. There are jagged edges in the data. Some scientists argue that we are seeing systematic errors in how we understand the dust in our own galaxy or the behavior of quasars. The battle is now between the signal and the noise. Every new observation is a filter, trying to separate the voice of the universe from the static of our instruments. As we move into the next phase of our journey, we will explore the alternative theories that are fighting for attention. If it's not decaying dark energy, what else could mimic this signal? Could gravity be leaking into extra dimensions? Could our position in the universe be special, creating an illusion of acceleration? The answers lie in the darkest corners of theoretical physics, where imagination meets the hard wall of mathematics. Let us imagine the moment the tide turns. For billions of years, the galaxies have been fleeing from each other, pushed by the dark wind. But as dark energy decays, gravity slowly tightens its grip. It starts subtly. The expansion slows to a crawl. Then, a moment of perfect cosmic stillness occurs. The universe holds its breath, and then the great reversal begins. The galaxies do not just drift. They are pulled back by the invisible ropes of gravity. This phase is the contraction. At first, it would be undetectable to the naked eye. Civilization would need sensitive instruments to see that the redshift of distant stars, the sign that they are moving away, is slowly turning into a blue shift. Blue shift means approach. The light waves are being compressed as the source moves towards us. The entire universe effectively begins to fall towards a central point, and we are falling with it. As the contraction accelerates, the night sky changes forever. Today, we see a mostly black void with scattered points of light. In a collapsing universe, the empty space between galaxies shrinks. Slowly, the faint smudges of distant galaxies would grow larger and brighter. They would become visible to the naked eye, not as points, but as swirling islands of light. The isolation of the Milky Way would end. The sky would become a crowded tapestry of neighbors. This beauty, however, is the herald of doom. As galaxies rush towards each other, collisions become frequent. But the real danger is not the collision of stars, it is the radiation. The cosmic microwave background, the leftover heat from the Big Bang, is currently a cold, invisible microwave radiation. But as the universe shrinks, this radiation is compressed. It gains energy. It shifts from microwaves to infrared, and then to visible light. Imagine looking up at midnight, but there is no darkness. The background of space itself begins to glow. At first, it is a faint, dull red, like the embers of a dying fire. But as the universe contracts to 1% of its current size, the sky turns a bright, angry orange. There is no night anymore. There's only the blinding light of the shrinking cosmos. The temperature of deep space rises from near absolute zero to the temperature of a summer day, then an oven. This is the fry before the crunch. Planets would not need a sun to be scorched. The sky itself would boil the oceans. Life as we know it would become impossible long before the matter is crushed. The universe essentially becomes a pressure cooker. The accumulated light of all the stars that have ever shone is trapped in a shrinking box, bouncing around and intensifying. It is a reversal of the thermodynamic flow. The cold sink of space is gone. This brings us to one of the most mind-bending paradoxes in physics, the arrow of time. We perceive time flowing forward because entropy disorder increases. A glass breaks, but it doesn't unbreak. But in a collapsing universe, does entropy reverse? Some early cosmologists, including a young Stephen Hawking, once speculated that in a contracting universe, time might run backwards. Rain would rise from the ground. Broken glasses would reassemble. While Hawking later corrected himself, admitting that entropy would likely continue to increase even during collapse, the idea haunts us. If the geometry of space-time is reversing, our perception of causality might shatter. Even if time doesn't physically reverse, the psychological experience of living in a world where the future is smaller than the past would be profound. We would be a civilization running towards a known finite wall of time. As the volume of the universe shrinks, black holes become the dominant predators. In the late stages of the crunch, supermassive black holes would merge at a frantic pace. These mergers would shake the fabric of spacetime so violently that gravitational waves would be strong enough to physically stretch and squeeze planets. A planet might be ripped apart simply by the gravitational song of distant monsters before it even hits its surface. Eventually, the density becomes so high that individual galaxies lose their structure. Stars are stripped of their outer layers. Then, atoms themselves are under siege. Electrons are pushed into protons. The distinct elements of the periodic table are crushed into a soup of neutrons. We are returning to the conditions of the first few minutes after the Big Bang, but we are arriving there with the accumulated baggage of billions of years of history. What happens at the very end? The singularity. In standard relativity, the universe contracts to a point of zero volume and infinite density. Mathematics breaks down here. It is a divide by zero error in the code of reality. But quantum mechanics suggests that a true singularity might be impossible. As we approach the Planck scale, the smallest unit of measurement, the graininess of space-time might resist infinite compression. This resistance is what fuels the big bounce theory we touched on. Imagine a ball hitting the floor. It compresses, stops, and then springs back. If the fabric of space has a limit to how much it can be squeezed, the big crunch inevitably leads to a new expansion. This means our Big Bang was not the beginning of everything, but merely the bounce from the previous universe's crunch. We are living in the rebound of a dead cosmos. The cyclical model, known as the eperiodic universe or conformal cyclic cosmology, offers a kind of immortality. Not for us as individuals, but for the process. It suggests that the decay of dark energy is a reset mechanism, a way for the universe to cleanse itself of entropy. In this view, the end is actually a cleansing fire that prepares the ground for a new beginning. It transforms the cosmic horror of death into a cycle of renewal. However, for any beings living near the end, it is small comfort. the transition is violent and absolute. No information can bridge the gap. No hard drive, no stone tablet, no DNA strand can survive the crunch. The next universe starts with a blank slate. The physical constants might be reshuffled. The speed of light could be different. The new universe might not even support life. It is a lottery that is drawn every trillion years. Could a sufficiently advanced civilization survive the crunch? Some futurists, like Michio Kaku, have speculated about escaping the universe. If we could master the energy of the collapse, perhaps we could tear a hole in space-time, a wormhole, and slip into a parallel universe or a baby universe before the door slams shut. It sounds like pure fiction, but if the walls of the room are closing in, checking for a window is the only logical move. This desperation highlights the ultimate difference between the big freeze and the big crunch. In a freeze, heat death, we slowly fade away, lethargic and cold, separated by infinite distances. In a crunch, we are brought together. We die in a crowded, hot, energetic frenzy. It is a death by fire versus a death by ice. The daily data suggest we might have booked a ticket for the fire, which is a much faster, albeit more violent, exit. But let's step back to the why. Why is dark energy decaying now? Some theories suggest that dark energy is interacting with dark matter. They are exchanging energy. As dark matter clumps together to form galaxies, it might be draining the energy from the vacuum. This coupled quintessence means the structure of the universe is consuming the very engine that expands it. The existence of galaxies like ours might be the reason the expansion is dying. This implies a symbiotic relationship between the contents of the universe and the space it occupies. We are not just passengers. The matter that makes us up is part of the equation that determines the lifespan of the cosmos. If this coupling is strong, the decay could happen exponentially faster than we think. The timeline could shift from billions of years to merely hundreds of millions. In cosmic terms, that is tomorrow. As we finish this chapter on the mechanism of collapse, we are left with a universe that is far more fragile than we believed. The solid ground of constant laws has turned into quicksand. The DESI observations have taken the safety rails off. We are drifting in a vehicle where the brakes might have just been slammed, and we are waiting for the whiplash to hit us. The stability of the last 13.8 billion years might have been a temporary anomaly. In the next part, we will explore the alternatives. What if DESI is wrong? Or worse, what if it's right? But the explanation is not decaying energy, but leaking gravity. We will look at modified gravity theories and the possibility that our universe is losing energy to a higher dimension. We will also discuss the profound crisis in cosmology and how scientists are desperately trying to patch the holes in Einstein's theory. As we scrutinize the DESI data, we must consider the alternative. What if dark energy is fine, but our understanding of gravity is broken? For a century, general relativity has been the undisputed king of physics, but it has never been tested on the scale of the entire universe over billions of years. The anomalies we see might not be a dying energy, but a sign that gravity behaves differently across vast distances. This is the realm of modified gravity. Imagine if gravity, like a rubber band, eventually gets tired. At small scales like our solar system, it works perfectly. But over the span of light years, perhaps its grip loosens or tightens in ways Einstein didn't predict. If gravity is stronger on cosmic scales than we thought, it could be pulling the universe back together without needing dark energy to decay at all. It's an illusion of decay caused by a misunderstanding of the rules. To solve this, physicists are turning to string theory and the concept of brain worlds. This theory suggests that our entire three-dimensional universe is just a brain membrane floating in a higher dimensional space called the bulk. Think of a piece of paper floating in a room. We are trapped on the paper. We cannot see the room. But here is the catch. While light and matter are stuck on the paper, gravity might be able to leave it. This gravity leakage solves a massive mystery. Why is gravity so weak? A tiny magnet can lift a paperclip against the pull of the entire Earth. It is absurdly weak compared to electromagnetism. If gravity is leaking into extra dimensions, drifting off into the bulk, then we only feel a fraction of its true strength. But if this leakage varies over time, it would look exactly like the expansion of the universe is changing unpredictably. If gravity leaks out, energy might also be leaking in. The DESI signal could be interpreted as an interaction with a parallel universe that is mere millimeters away from ours in a fourth spatial dimension. If two brains drift close to each other, their gravitational fields would interact. The slowing down of our universe could be the result of a neighboring universe pulling on us, acting as a cosmic break through the void between dimensions. This scenario, often called the ekpyrotic scenario, suggests that the Big Bang was actually a collision between two of these brains. Now, billions of years later, they might be drifting apart or preparing for another kiss. The fluctuations in dark energy are essentially the ripples of this interdimensional dance. We are detecting the shadows of a reality that is geometrically impossible for us to perceive directly. Let's ground this back in what we can measure: dark matter. We assume dark matter is cold and collisionless, that it doesn't interact with anything except through gravity. But the interacting dark sector theory challenges this. What if dark matter and dark energy are not separate? What if they can transform into each other? Imagine dark energy decaying into dark matter, like steam condensing into water. If dark energy turns into dark matter over eons, two things happen simultaneously. The push to expand, dark energy, weakens, and the pull to collapse, dark matter, strengthens. This double whammy fits the DESI data frighteningly well. It implies the universe is a cannibalistic system where the vacuum is slowly being eaten by the structure within it. The universe is converting its potential future, expansion, into present mass, gravity. We see evidence of strange behavior in the cosmic voids, the vast, empty bubbles between galaxy filaments. These voids are the dominant feature of the universe by volume. If dark energy is changing, the voids should be evolving differently than we predicted. In a decaying model, the voids stop growing. They might even begin to be crushed by the surrounding walls of galaxies. We are currently analyzing the shapes of these voids for clues. The Boat's void, often called the Great Nothing, is 330 million light-years across. If the universe is slowing down, these voids are the first places where the expansion stalls. They are the canaries in the coal mine. Recent surveys suggest that the outflows of matter from these voids are not as fast as they should be. The emptiness is not pushing back as hard as it used to. The pressure of the nothingness is dropping. There is an even more radical interpretation that borders on metaphysics, the holographic principle. This theory states that all the information in a volume of space can be described by the boundary of that space. If the universe is a hologram, the resolution of reality depends on the surface area of the horizon. As the universe expands, the information content changes. A glitch in dark energy could be a pixelation error. If we are living in a simulation, a hypothesis taken seriously by some philosophers and physicists, the variable dark energy could be an optimization protocol. To save processing power, the simulation might slow down the expansion of distinct regions that are not being observed or are too computationally expensive. The DESI anomalies might be the artifacts of a system resource management that we were never meant to notice. Regardless of whether it's aliens, simulations, or brains, the standard model of cosmology, lambda CDM, is bleeding. It has survived for 25 years, but it is now held together by duct tape. We have added inflation to explain the beginning, dark matter to hold galaxies together, and dark energy to push them apart. None of these have been directly detected in a lab. We only know them by their effects. Critics argue that we are adding epicycles, complicated corrections, to save a flawed theory, just like astronomers did to prove the Earth was the center of the solar system. The decay in dark energy might be the final straw. It might force us to abandon the idea of dark components entirely and rewrite the laws of gravity from scratch. We are on the verge of a paradigm shift that happens only once every few centuries. The judge and jury for these theories will be the next generation of telescopes. The Euclid mission, launched by the European Space Agency, is currently mapping billions of galaxies. Its goal is to measure the shape of the universe with even higher precision than DESI. If Euclid confirms the decay signal, the debate ends. The variable nature of the cosmos becomes a fact, and we must prepare for the implications. Euclid looks at the distortion of galaxy shapes caused by gravity, weak lensing. If gravity is leaking or changing, Euclid will see it in the warped images of distant galaxies. It creates a tomography, a 3D scan of the dark universe. We are expecting the first major data release soon. It is a race against time to understand time itself. Every day without an answer is a day we live in ignorance of our ultimate fate. Let's pause to appreciate the irony. We used to fear the big freeze. The idea that the universe would expand forever until all stars burned out and entropy won was the ultimate depressing thought. It meant nothing we did mattered because it would all be erased by cold distance. The Big Crunch, or decaying universe, offers a different kind of horror, but also a strange connection. It means we are part of a finite closed story. A closed story has a climax, it has a resolution. If the universe ends in fire, it implies that the energy is conserved and concentrated, not wasted. For humanity, this shifts our long-term perspective. We are not drifting into oblivion. We are racing towards a wall. It changes the urgency of our existence. If time is finite, then this moment, right now, becomes infinitely more precious than in a universe of infinite waste. As we approach the final segment of our journey, we must ask, what does this mean for life? If the universe is changing, can life adapt? We are biological machines evolved for a specific set of physical constants. If gravity gets stronger or electromagnetism shifts, our biology might fail. But life is resilient. Just as we crawled out of the oceans, perhaps we will learn to swim in a changing vacuum. The history of science is the history of humans realizing they are not the center of the story. We are not central in space, and now we realize we are not central in time. We live in a transient era, a fleeting Goldilocks zone of cosmic history where the expansion is just right for stars and planets. But as we will see, this fragility might be the very reason we are here to observe it at all. The Anthropic principle has a dark side. The Anthropic principle asks a simple question: why is the universe exactly the way it is? The answer is tautological but profound. Because if it were any different, we wouldn't be here to ask the question. We exist in a universe that permits life. If dark energy had been slightly stronger in the past, galaxies would have been torn apart before stars could form. If it were weaker, the universe would have collapsed before life evolved. We seem to be the winners of a cosmic lottery. But the new data on decaying dark energy adds a twist to this principle. It suggests we are not just in the right place, but in the exact right time. We are living in the brief window where the universe is habitable. If the decay accelerates, the window closes. This implies that intelligent life might be a fleeting spark in the dark history of the cosmos, destined to burn out quickly. This leads to the coincidence problem. Why do we live in an era where the density of dark energy is roughly equal to the density of matter? For most of cosmic history, this wasn't true. In the early universe, matter dominated. In the far future, dark energy should dominate. But we are here, right in the middle, at the tipping point. The DESI results suggest this isn't a coincidence, but a mechanism. The universe might be tuning itself. If the universe cycles, expanding and contracting, perhaps life only emerges at the specific phase of the cycle. We are the children of the autumn. We appear just as the cosmic summer ends and the leaves begin to fall. This perspective shifts our role. We are not the masters of the universe. We are its witnesses. We are the eyes that the cosmos grew to see itself before it goes blind again in the coming collapse. This brings us to the Fermi paradox. Billions of stars, billions of years, yet we hear only silence. Where is everyone? The Great Filter theory suggests that there is a barrier that prevents civilizations from surviving. A decaying universe offers a grim solution. Maybe civilizations don't die out because of war or disease. Maybe they are wiped out by the instability of the universe itself. Perhaps they saw the crunch coming. If advanced civilizations discovered millions of years ago that the universe is unstable, their silence makes sense. Why broadcast your location if the walls are closing in? Or perhaps they have already left. If Type 3 civilizations exist, capable of harnessing the energy of galaxies, they might have used that energy to escape to a stable dimension, leaving the dying universe behind like a sinking ship. We are the ones left on the deck. There's a statistical concept called the doomsday argument. It uses probability to estimate how many humans will ever be born. If we assume you are a random human in the total history of the species, you are likely born halfway through the timeline. This statistical logic predicts that humanity will go extinct sooner rather than later. A collapsing universe aligns terrifyingly well with this mathematical prediction. It suggests that we are not at the beginning of a long Star Trek future spanning millions of years. We might be nearing the end of the show. The fact that we are discovering the instability of the cosmos now, just as we become a spacefaring species, is suspicious. It feels like a final puzzle piece falling into place before the game ends. It forces us to ask, is knowledge of the end the final achievement of intelligence? Let's reconsider the psychological impact. If the universe is finite, does it make our actions meaningless? Nihilism is the easy trap. If it all burns, why build anything? But there is another view. The Japanese concept of mono no aware, the pathos of things. It is the appreciation of the transient nature of beauty. The cherry blossom is beautiful because it falls. A universe that ends might be more precious than one that lasts forever. An eternal universe is a cage of infinite repetition. Everything that can happen will happen infinite times. It dilutes meaning. But a finite universe, one that has a story with a beginning, a middle, and an end, gives weight to every moment. If this is the only time life will exist, then our art, our love, our discoveries are singular events. We are etching graffiti on a wall that will soon crumble, but we are the only ones who can hold the chisel. Consciousness itself might be the universe's defense mechanism. Quantum mechanics tells us that the observer affects reality. The quantum Zeno effect suggests that observing an unstable particle can prevent it from decaying. Could it be that by observing the universe, by measuring the dark energy, we are actually influencing it? Are we, the observers, keeping the bubble from popping just by looking at it? This is highly speculative, bordering on mysticism, but in the face of the unknown, the line between physics and philosophy blurs. If the universe requires an observer to exist, then the end of life means the end of the universe. The big crunch doesn't happen when the stars collide. It happens when the last eye closes. In this sense, our survival is not just for us. It is a duty to existence itself. We are the guardians of the timeline. So what do we do with this information? We are trapped on a rock, orbiting a ball of gas, in a universe that might be running out of battery. The first step is verification. The scientific method is our candle in the dark. We must wait for the Euclid and Roman telescopes to confirm the DESI data. We must rule out every error, every smudge on the lens. Skepticism is our shield against panic. We cannot surrender to do without proof. But while the scientists measure the stars, the rest of us must measure our values. The potential of a big crunch strips away the arrogance of immortality. It reminds us that we are part of a fragile ecosystem. It connects us to the ancients who feared the sky would fall. We thought we had solved the cosmos, that we had tamed it with equations. The universe has humbled us again. It remains wild, unpredictable, and dangerous. If the worst is true, and the collapse has begun, we have time. The crunch is not tomorrow. It is billions of years away. We have time to evolve. We have time to become the Type 3 civilization that can manipulate space-time. Theoretical physics allows for the creation of baby universes in a lab. If we cannot save this house, perhaps we can build a lifeboat. The ultimate goal of life might be to become the seed for the next Big Bang. Imagine a civilization that encodes its knowledge, its history, its essence into the fabric of a black hole or a gravitational wave, sending it through the crunch to the other side. A message in a bottle thrown into the cosmic ocean. It shifts our purpose from mere survival to legacy. We are building the genetic code for whatever comes next. We are the ancestors of the next reality. This connects back to the very first human who looked up and wondered. The story of science is a story of expanding horizons. We moved from a flat Earth to a solar system, to a galaxy, to an expanding universe, and now, potentially, to a dying or cyclic one. Each step is terrifying, but each step is true. We should not fear the truth, no matter how heavy it is. A finite universe is a truth we can handle. In fact, it might be the push we need. If we know the resources are limited, if we know that time is finite, maybe we stop wasting it. Maybe we treat our planet and each other with the urgency of a crew on a sinking ship who realizes they are all they have. The cosmic decay is a mirror. It forces us to look at our own mortality and find meaning not in duration, but in intensity. As we prepare to conclude our investigation, we stand at a crossroads. One path leads to a static, boring, eternal death by ice. The other leads to a dynamic, fiery, mysterious rebirth. The DESI data has pointed us towards the fire. It has made the universe interesting again. It has proven that the book of nature has pages we haven't even cut yet. The mystery is alive, and it is breathing down our necks. In the final part of this series, we will summarize the evidence, look at the immediate future of this research, and leave you with the final thoughts on how to live in a universe that might be dying. We will synthesize the physics, the philosophy, and the future into a final verdict. The story of the universe is not over. It is just getting to the plot twist. We have traveled from the edge of the observable universe to the quantum foam of the vacuum. We have seen that the ground beneath our feet, the very stability of space-time, is shifting. The DESI findings are not just data points. They are a wake-up call. They tell us that the story of the universe is far from over. In fact, the most dramatic chapters might be yet to come. The era of precision cosmology has turned into the era of cosmic uncertainty. The narrative has shifted from the big freeze, a slow, melancholic fade into darkness, to the big crunch, a dynamic, violent, and purposeful reunion of all matter. This shift matters because it changes the definition of our universe from a wasteland to a machine that processes energy, creates structure, and perhaps eventually resets itself. We are not living in a graveyard. We are living in a chrysalis waiting to open. The balance between dark energy and gravity is the most delicate dance in existence. For decades, we thought dark energy had won, pushing everything apart forever. Now we see gravity fighting back. It is a cosmic tug-of-war. If the vacuum energy is indeed decaying, gravity will eventually reclaim its throne. The scattered children of the Big Bang, the stars, the planets, the dust will be called home. It is a return to unity. This reunion implies that separation is temporary. The loneliness of deep space, the impossibility of traveling between galaxies, might just be a phase. In the far future, the universe will become smaller, hotter, and more connected. The distances that currently imprison us will shrink. While this spells the end of biological life as we know it, it also represents the ultimate convergence of information. Nothing is truly lost. It is just compressed. What should we watch for in the coming years? The scientific community is currently analyzing the systematics of the DESI data. They are checking for dust, for calibration errors, for anything that could be a mirage. But parallel to this, the Euclid Space Telescope is sending back its first deep field images. By the late 2020s, we will have a definitive answer. We are the generation that will know for sure how the world ends. If the signal is confirmed, expect a revolution in physics. We will see a rush to unify quantum mechanics with general relativity. The theory of everything will no longer be a luxury. It will be a necessity to explain the decaying vacuum. We might discover new particles, new fields, or extra dimensions that were hiding in the math all along. The crisis in cosmology is actually a golden age of discovery disguised as a problem. Let's revisit the Big Bounce. If the universe resets, it answers the question of before the Big Bang. There was no before, only a previous now. It suggests an eternal heartbeat of expansion and contraction. This makes our universe infinite in time, even if it is finite in space. We are part of an infinite chain of universes, each one slightly different, each one an experiment in existence. We are iteration number X in the grand design. This idea takes away the fear of oblivion. We are like waves in the ocean. The wave rises, crashes, and disappears, but the water remains. The energy that makes up your body, the electrons in your brain, have likely existed in previous cycles and will exist in future ones. We are recycled stardust, momentarily conscious, before being cast back into the cosmic fire to be forged into something new. So is the universe dying? Dying is a human word. It implies a tragic end. A better word is evolving. The universe is changing its phase. Just as water turns to ice, the cosmos is turning from expansion to contraction, it is a natural process. To fear it is like fearing the sunset. The sunset is the precursor to the dawn. The Big Crunch is the necessary condition for the next Big Bang. It is the cost of creation. However, the fragility of our current era remains. We exist on a razor's edge. This knowledge should make us cherish our Goldilocks moment. We are the universe's way of understanding itself before the lights go out. Every scientific discovery, every piece of art, every act of kindness is a defiance against the coming dark. We are the memory of the universe, and we must make sure that memory is worth keeping. As we sit here on this small blue dot, the galaxies above us are already slowing down. The great engine is decelerating. We cannot feel it, but the equations tell us it is happening. It is a reminder that stability is an illusion. The only constant in the universe is change. And perhaps, the only purpose of the universe is to experience that change through the eyes of conscious beings like us. If we are the observers, then our observation matters. By looking at the stars, we give them meaning. A universe without life is just a physics problem. A universe with life is a story. And even if the story has an ending, that doesn't make it any less beautiful. In fact, the ending is what gives the story its shape. We are writing the middle chapters of the greatest story ever told. In the grand scheme, the end is billions of years away. We have time to explore, to expand, to learn. We might even find a way to escape the cycle. But whether we escape or not, we have already achieved something miraculous. We have awoken. Matter has organized itself into a form that can look back at its creator and ask why. That question is our legacy. It is the echo that will ring out even as the walls close in. The dark energy findings are a gift. They have shattered our complacency. They have forced us to look at the sky with new eyes, not as a static painting, but as a dynamic, breathing, dying, living entity. It has brought the mystery back to science. And where there is mystery, there is hope. Hope that we are missing something. Hope that the next discovery will be even wilder than this one. As we conclude this series, I want you to look at the night sky tonight. Really look at it. The light you see has traveled for millions of years to reach your retina. It is a message from the past. But now you know it is also a message about the future. The stars are telling us that nothing lasts forever, and that is okay. It is the fleeting nature of existence that makes it beautiful. Thank you for joining me on this journey into the dark heart of cosmology. We have peered into the abyss, and the abyss has stared back, but it didn't stare back with malice. It stared back with possibility. The universe is not a cold, dead place. It is a dynamic, evolving mystery, and you are a part of it. You are the universe experiencing itself. If you enjoyed this deep dive into the fate of the cosmos, please consider subscribing to Nightlight Science Stories. We explore the boundaries of what is known and what is possible. Light a candle in the dark with us. Share your thoughts in the comments. Do you prefer the big freeze or the big crunch? Which ending scared you less? I read every comment, and I'd love to hear your theory. Remember to click the notification bell so you don't miss the next time we unravel the fabric of reality. There are infinite stories in the naked city of the universe, and we have only just begun to tell them. Until next time, keep looking up, keep wondering, and don't let the darkness extinguish your light.